So welcome. At the very beginning, I want just to repair one small mistake, which was yesterday on the blackboard. That you remember when we spoke about reducible representations that we introduced some subspace, and this is from the whole space. So altogether it is whole vector space, and W is subspace, and we used adapted basis and computed the matrix. So here it was rho AB, EB plus rho G acting on EI, AI, EI, and here it is rho G IA, EA plus rho J IJ AJ. And the block matrix here is BA, but here is this IA. So it was reversed on the blackboard. Here is AI block, and here is JI block. Because the upper index is the first one, and the first one goes down in the matrix. Yes. So it was reversed that, and because this is 0 for irreducible representation, it was explained yesterday. So the 0 should be here, not here. It is a detail. I think that this mistake you were able to find, but just to make it correct. Okay, so now I will go on to finish the Schur's lemma. That it is treated the intertwining operators, so A, from some V1 to V2 where we have representations, namely here rho 1 and here rho 2. And intertwining operator by definition fulfills this diagram. So we have an equation that first A and then rho 2 G is the same thing like first rho 1 G and then A. You remember. And Schur's lemma is interested in the case when this Schur's lemma for rho 1 and rho 2 irreducible. And it specifies somehow that what can we say about this A in the case when both these operators, these representations are irreducible. And there was a statement, so this is already not from these topics, that in this case we have just two possibilities. Either rho 1, rho 2 are not equivalent, and then A is necessarily 0, or they are equivalent, they are equivalent. And then, of course, A is isomorphism. This is the definition of what does it mean to be equivalent. So the interesting part is that there are just two extreme possibilities for this A. Isomorphism and zero operator are two extremes of operators. Yes? There are many possibilities between these cases. So only these extreme cases can be true if we have irreducible representations. This was done yesterday. And also the proof was done. The proof is based on the fact that you make an observation that these two subspaces are invariant. It is a simple check. Then, if they are invariant and our representations are irreducible, this means that both of them are either the whole subspace or zero. And the whole subspace here is, the whole space is V1 and here is V2. And now there are four possibilities, two on both sides. And if you check what does it mean, for example, possibility ker A equals V1 and A equals V2 and so on, so you'll find that these four possibilities are compatible with this statement, that it proves this statement. Now there is a second part of this theorem, or maybe second theorem, which treats irreducible and complex. Irreducible still, and complex representations. So it is the second part of the first theorem, that they are complex and equivalent. So these two properties. So complex means, once again, I told it yesterday, that these vector space are complex vector space. That is, the matrices are, when you introduce a basis, you will have a matrices, and matrices can be complex matrices. And if they are equivalent, that means that A is isomorphism. Yes? So there exists an isomorphism. Now you see from here that if A is isomorphism, that also some multiple is a solution of this equation, and non-zero multiple is another isomorphism. Yes? So the fact that if there is an isomorphism, it is not unique, is clear because by product with a number, complex number lambda, you will see that there is a freedom of this type. It is a specific case of more general statement that these operators produce a vector space. So we have a vector space of intertwining operators always. So of course multiple is possible. But the statement here is that in this case, this is the only freedom in the operator. So this is clear that this is a freedom, but it is not clear that you have some other dimension of the vector space of intertwining operators. So the proof can be done like that imagine you have B, another one. Then, because it is a vector space, we can construct this C. So we want to prove that this B is just lambda B, lambda A, yes? So let's assume there is another B, and if we were lucky at the end we will see that this B is just lambda A. So we construct first some C of this structure with arbitrary lambda, it is possible, arbitrary complex lambda. we will see why complex is important in the proof. This is possible because now the operators are in the complex vector space, so this makes sense. If this will be complex in real vector spaces, it is a problem, yes, that you cannot do it. Now, we can compute determinant at the level of matrices already of this and put it 0. Then, what does this mean? That we, how put it 0? By appropriate choosing of this lambda. This is some polynomial equation for lambda. We can solve it. It is some polynomial of lambda equals 0, if you think it over. And now, it is critical that lambda can be complex, because polynomial equations not always have real solutions. Quadratic equation, for example, lambda squared plus 1 is 0, has no real solution. We need to invent I for solution of this equation, yes? So, because of this fact, that we need to find such lambda that this expression should be 0, and this is only possible for lambda complex in general. If we find this root of this equation, and it is guaranteed that there exists, then this matrix is not invertible. Yes, because determinant is 0. But if it is not invertible, it cannot be equivalence. It is not isomorphism. And if it is not isomorphism, it should be 0 by the first part of the theorem. Yes? So if this is 0, we see that A is lambda B. So this is the second part of the, it is still Schur 1, but I in the book. The first, this was I part of the lemma. And now there is a very important consequence. And this consequence, so now I will write Schur 2, but this nomenclature is not important, of course, that what is 1, what is 2. Simple statement done by Schur, that do this for the case of two equal representations. What does it mean now that some operators intertwining between the same operator, the same representation? So it means that this equation holds for lambda 1 equal lambda 2 equal lambda. So this is assumption now, that let's study simple particular case when we have two representation given by just one. Now, this can be read in another way, simply that rho g commutator with A is 0. Yes, it is not possible to write it here, because they are different guys here. But because they are the same guys, it is just a commutator. So when we say that A is intertwining operator for rho, it is the same like to say that the intertwining operator is commuting with all operators of your representation. So it is completely another set of words. But it has the same meaning here. Yes, that if you find an operator which commutes with all operators of the representation, all, I mean that for all G, yes, then the statement is that this A should be nothing but just lambda, a multiple of unit operator. Now, it is a simple consequence of the last theorem. Why? Because unit operator is solution of this operator, clearly. Yes? Unit operator commutes with all operators. So we have one solution, and all other solutions are just lambda of any one solution. So we see that because A equal 1 is a solution, that all other solutions are just multiples of this unit operator. So this is the most famous statement, which is called in physics textbooks that Schur's lemma, including the green book of quantum mechanics, which you have as a basic book on your quantum mechanics course. You can find Schur lemma somewhere there. In the study of representations of SO3, under the title that symmetries and rotations and something like that. It is in the summer semester, not in the winter semester. So we will see application of this fact, very important, which is done there. Now, there is another important consequence. So this is the most important consequence of the first part of the lemma, and it is the famous, most famous conclusion. And now there is another very important conclusion, that imagine that our group is commutative. That means that G1, G2 is G2, G1 for all elements. And such groups are also called abelian, because mathematician Abel did something with them. Now apply rho to this equation that represent this equation with some representation. We'll have rho G1, rho G2 equals rho G2 and rho G1. Now, G1 and G2 are arbitrary. Yes? So we can read this equation that rho G1 commutator with rho G2 is 0 for all G1 and G2. So fix, for example, G1 and call this A. What does it mean? That A commutes with all operators of the representation. So we are here. So what does it mean? That this operator should be just some multiple of unit operator. But this multiple can be different for various group elements. Yes. Lambda, in principle, depends on this G1. So in general, we see that rho G is some lambda G times unit operator. But now comes, this is true for any commutative group. And now if rho is irreducible, this is true also without irreducibility assumption. But if it is irreducible, we can conclude from that the dimension of V is just 1. Can you tell me why it is so? So this is in general any dimensional representation. In any dimensional representation, you have this result. This is a unit operator in any dimensional V. It is some rho V dimension n. But if it is irreducible, we know that the dimension of this V is just 1. Can you tell me that why? it is based on the definition. What does it mean, irreducible representation? So can you tell me what does it mean, irreducible representation? That there are no what? Reducible means that there is some W, which is which?
Which is a subspace of the origin of V, where the law operates like within it.
Yes, so it is called invariant, exactly. So irreducible means that there are no invariant subspaces except for everything and zero. Yes? But this operator acts in such a way that any subspace is invariant. Yes, because it is just multiple of one. So if you have any subspace and apply this operator, you just multiply the vectors in this subspace, and it cannot go out of the subspace. Yes? So think it over, that this operator preserves all subspaces. So it is not now possible that you have no invariant subspaces and you have operators which preserve all subspaces, except for the case when the dimension is just one. Then there is no contradiction. If dimension is 2, 3, and so on, it is a contradiction. Think it over. So this is very important, this result. What it says, that whenever you have a commutative group and you want to use this, so it is necessarily irreducible complex representations. If you want to study irreducible and complex representations, then this holds, and it should be there should be no invariant subspace. So the dimension should be 1. This fact that all irreducible complex representations of any commutative group are just one-dimensional greatly simplifies the way how to find them, all of them. Yes? For example, the important, maybe most important, U1. G equals U1. It is commutative group. They are one-by-one complex matrices with some property. So because they are one-by-one complex matrices, they commute. The elements look like e to I alpha, or complex numbers of modulus 1. They are elements, and the multiplication is multiplication of complex numbers. It is commutative. So if we want to find a representation, we want to find the mapping that this Z, this of the form e to E alpha, so this is Z equal, so goes to rho of Z, this is some representation, but if you want to find irreducible representations, this should be one by one matrix. So such object like this Z, yes, this is one by one matrix, and by irreducible representation, it should go to some possibly other one by one matrix. So one complex number goes to other complex number. From this assumption and from homomorphism, and that unit element goes to unit element and continuity, you can find very easily, explicitly how it looks like, all possibilities. It is an exercise in the book. I don't remember the number, but it will be in the offer for exercises. And the result is that there are representations labeled by integer, any integer, and the result is that if you apply them on an arbitrary group element, you will obtain En alpha, or at the level of Z, it is Z goes to Z to N, yes, with integer N. This is both one-dimensional, irreducible, and continuous, and I don't know what, homomorphism. It is the only possibility. That means that there are infinite number of possibilities, but very simple, labeled by just one integer. So you can check it, you can solve this exercise and tell it to us that how is it all. There is a hint, of course, in the book. So it is quite simple exercise. But this result is very important, yes, that because we know that they are one-dimensional, then it is quite simple problem. We solve this problem, and the result is this one. So if you represent the group element e to I alpha, the representation matrix is e to I n alpha. This number n, which labels any particular representation, plays an eminent role in physics, and it is called usually charge. It is charge of something. They are so-called U1 charges. Electric charge is an example, but there are also other charges, and all these U1 charges work in this way, and in this way we can see somehow that this n is the number. There is some basic charge, and n is how many basic charges is your charge, particular. Yes. So this is, I think, everything we should know from the lecture about this Schur lemma. There are some exercises like this one. And now they are intertwined Schur lemma. It is number 3 from the end. Number 2 from the end is invariant scalar product, Killing-Cartan, and so on. So another topic, but still in this week, so about representations. The next week will be already manifolds, tangent space, vectors, and so on. Yes. So we finish this linear algebra more or less. Not completely, because Lie groups are manifolds, but representation theory is in some sense Lie algebra up to some level. So now we introduce important concept, invariant scalar or scalar product. So we know what is scalar product. It is given by some bilinear form in V with some representation. So these two guys are from V for some vector space, and this is their scalar product given by inserting them to some bilinear form, symmetric bilinear form, and so on. Now, so it is the structure. It is the structure that VH, that we have a vector space, and in this vector space we have a bilinear form, so we are able to compute scalar products. But as is seen here, in the same space there is a representation of some group. And we want to interpret it as a triple which is compatible. So we have this triple. At the same time, in our vector space, we have we have this scalar product, this H, and we have a representation of some group. That means we can construct rho G operators for all G. What can be the compatibility? That if you compute this scalar product, you should obtain the same number as if you compute the scalar product of other two vectors the maps of these two vectors with respect to representation operator. You choose some G, obtain rho G, and then act in on V and W, and once again compute the scalar product. So you compute altogether two scalar products at the beginning with original V and W, and at the end with transformed V and W. In general, if this is not, there is no compatibility, they are unrelated numbers. But compatibility means that they should be related numbers. So this is that we want this to be true, of course, for any what? Any G and any V and any W. Yes? So we should, if we want to have invariant scalar product, it should be invariant in this way. This is the compatibility. One can write this in basis, inserting EA and EB, we get HAB here. It is the matrix or components of this bilinear form. And here it should be what? H computed on rho G A C E C and rho G acting on E or rho G B D E D. And putting scalars out, we will obtain rho G A C rho J G A B D and H on CD, so HCD. So it is component expression of the same fact. Here is abstract expression of the fact here for matrices. You have matrices of this representation, matrices of this bilinear form, and there you can think over what kind of matrix product is here. It is simple. So it is the same fact written in the language of matrices. And now it can be taken in two ways, that either you have fixed H and you find some representation which preserves it, or more often that you have some representation and you try to find this H which is good for this representation. Yes? Sometimes such situations comes from the heaven, that you directly obtain some scalar product somewhere which looks quite natural, and you check it and you obtain the fact that yes, it is good, it is invariant. Yes? Sometimes you have not it directly and you can compute it somehow. So now I will show how it can be computed for finite groups. It is just for inspiration for us, because this course is not about finite groups. Theory of finite groups is interesting in its own case, but here it is just for inspiration, that for finite groups there is some idea, and we can then tell that what the idea says for Lie groups. So our group has a finite number of elements. First is unit element, which we call G1, and then G2, and at the end some Gn. So altogether n elements. Now we take any scalar product H0, some zero approximation, which is arbitrary, but scalar product. Yes? And from this, you would like to obtain somehow the scalar product which will be already good. So this is arbitrary, not good maybe. And by some procedure we want to somehow optimize it or recompute and obtain the scalar product which will be already a good one, that means invariant. So it turns out that it can be done in following way, that we define the final scalar product as 1 over n H0 on rho gk applied on V, rho gk applied on W, and to sum this from k from 1 to n. So what we do, we apply all group elements through this representation. All group elements, because there is summation of over the group. Add these arguments, sum the result and divide by n. Can you tell me that what procedure is done if you sum over some elements and divide by the number of elements? What do you do? What kind of procedure? Do you know that arithmetic mean or something like that? What is it? You have several numbers and you sum them and divide by the number and you will obtain that the arithmetic mean is this. So this is the arithmetic mean over these results. Yes? Nothing more. And it turns out that it helps. Yes? So we can now check that this result is already good, directly. So what do we want? We want that it is invariant, where it is here, with respect to application of any element. So any is one of them, some say G2. Yes? But you will see that the 2 is not important here. So we want to compute this and to prove that it is without these operators. Yes, that the result is here that you can put away this rho g. Yes, it is the property already. So now, what is it? 1 over n sum over k from 1 to n of what? Of h0, and put rho g2v instead of v. So it is rho gk applied to v, which is now rho g2, and then v. And the same here, first rho gk, and instead of w, rho g2 w. Because this is a homomorphism, it is rho of gk and g2. And the same here. So there is a summation over rho, but not gk, but gk, g2. And now imagine that you have all group elements and multiply them from the right by g2. Do you know, take this as a set, yes, as a set with n pieces. Then multiply it from the right by g2. What do you obtain? Which set? You obtain some other elements, yes? For example, here you will have g2, and g2 is normally here. But then you obtain g2, g2, g3, g2, and so on. And what is it all together? The same set. It is not completely trivial. It is a property of groups. You should check. So check that all those groups are just all those groups, maybe reordering. Yes? We will actually prove it in several weeks, we will study something which is called left and right actions of groups somewhere. Very, very nice subject. And this is a kind of action which is called right translation. Right translation on the group is exactly this. And right translation is an action, and each action has an inverse action. That's why this should have inverse, that's why it should be just a permutation. So this is the idea, we will have it. So if it is not clear to you that these are all group elements just reordered, wait and we will see it, or do it yourself. So what does it mean? That it is the same formula like that, but the sum is not in the order 1, 2, 3, 4, but maybe 2, 5, and so on. But the sum is still the same. So it is this expression, that means this expression. And this is the end of the story, yes? This is HVW. Now, what about Lie groups? What should be instead of this sum and division by n? We should compute some mean value where instead of sum we will have what? We have experienced in mathematics. So sorry? Integral. Some integral, okay. So here should be, for Lie groups, some integral over the Lie group, yes? Lie group is a manifold, so it should be some integral over some manifold. But it turns out that for integration over manifold, if you have some function and you want to integrate it, you need something like that, some volume element. And there are infinite numbers of volume elements in general. We don't know it, but we will learn next year. It is in chapter maybe 7 or in the book. So in mathematics physics 2, when we will study differential forms, we will learn something about this dv. And we will see that there are infinite number of dv's. Some of them are more interesting, some of them are not very much interesting. And here, there is a question that if there are infinite number of possibilities to integrate over Lie groups, which in particular should I choose for obtaining this result? And it can be solved quite easily if we are educated in differential geometry at Lie groups, which we are not, yes, not yet. But at the end of the next year, we will learn how to integrate over groups, and we can solve this problem. It is not a complicated problem. It can be solved. There should be some very specific volume element in order to repeat this. But there is another danger that if you integrate over some manifold, you can, and this is much bigger danger, that you can obtain sometimes infinity. If you have some function and do integral over the manifold R, for example, you can obtain infinity. And infinity is not very good scalar product. That scalar product which gives you infinity is not very useful. Yes? So this is real danger, that if your integration gives you infinite number as a scalar product, it is not very interesting, and that's why it is a big problem. And this problem is solved when these manifolds are so-called compact. So for the case of groups, it can be solved when your groups are as manifolds, compact manifolds. So the theory of representations of compact Lie groups is very similar to theory of representation of these finite groups, because you just replace this sum, which is well known in finite groups, by appropriate integral, and this result of this integral is a finite number because it is compact manifold. So it is more or less the same thing. Yes? It was done at the beginning of the 20th century. So the theory of finite groups was done at the end of 19th century. and by some wise mathematicians, it was then replaced on a theory of compact Lie groups. It is a big theory, but more or less simple and well known. The theory of non-compact representation of non-compact Lie groups is much more complicated because we have no scalar product, and with invariant scalar product, many things cannot be done. So there is a lot of wisdom in this direction, but it is more complicated because we have these tools which we have for representations, usually, for finite ones. Okay, this is the concept that invariant scalar product, this is what does it mean? Here, how you can produce such invariant scalar product from some arbitrary start, limitations that on Lie groups we can have problem sometimes. And now the story which is called Killing-Cartan scalar product, which is very important. For example, it works in gauge theories. You remember that a lot of things with groups has an application to gauge theories, and gauge theories are very successful in theoretical physics, so we would like to understand them. Killing-Cartan form, it is called usually, and it means bilinear. But usually it is called the Killing-Cartan form. So it is some bilinear form defined, it is a bilinear form in vector space which is Lie algebra. So it is something like that. K Killing-Cartan, more killing than Cartan, but by sound also Cartan, this K. And these are vectors from Lie algebra. And it should be some number, and it should be symmetric, bilinear, and so on. And first, take an operator adjoint of X. It is adjoint representation of Lie algebra, this guy. So if you put here X, as is here, it is an operator already in Lie algebra. Here is the same guy for another element of Lie algebra. And here it is composition. First operator, then the second on the result. And now we should make something which is called trace of this operator. This is altogether a linear operator in Lie algebra, composed of two smaller linear operators. Now, what is a trace? It can be simply written in terms of tensors. That imagine we have an operator from V to V. Take a basis, EA, in V, and EA in V star in the dual space. And now the trace, by definition, is the object EA, A on EA, with summation. What is it? This is the matrix AAB, EB. So it is also ABA, EA, EB. This is delta, and delta with this guy gives you AAA. So it is what we know already. What is it? What is this? If you have a matrix and compute this, what is in layman language? Sum of diagonal elements. Yes, here is the sum of diagonal elements. And for us, it's quite interesting that it can be written like that, especially for the fact that from this formula, also from here, but from this formula, it is clear that you can check it clearly and easily that it doesn't depend on the choice of this basis. There is a choice of this basis. This is already automatic. Yes? So if you choose here another basis, you should also choose this because it should be dual, and some matrices will cancel them, and you will see that this expression does not change with the change of basis, so it is something interesting. The trace of linear operator is interesting object. So in this sense, we have this trace here. Now, the properties. Adjoint representation is a representation. So, among other things, there are more properties also, but this is important, that the right-hand side here is linear with respect to this x. First, the inside of trace is linear because of that. Then the trace is linear itself, check. This is the trace of A plus lambda B is the trace of A plus lambda trace of B, either from this formula or by simple thinking that what does it mean, these diagonal elements. So that's why this number linearly depends on x. Also, it linearly depends on y. So this is bilinear form, the first observation. Yes, we really define the bilinear form. Then the claim is that this is a symmetric bilinear form. So where from it is visible that it is symmetric. What happens if we interchange x and y? So you see that interchanging of x, a1, here will be y, here will be x, but it can be interpreted that we made cyclic permutation of these two operators. Yes, that x is somehow glued to this Ad, and put the complete guy here and complete guy there. And what is the property of the trace? Right from this definition, the trace of A, B, and so on, C, is the trace of C, A, B, and so on. So going here. So it is invariant with respect to cyclic permutation, this trace procedure. And what does it mean for just two elements? That it is invariant with respect to changing of this element. So we can change this and we obtain still the same. Under the trace, these operators give the same when interchanged. So from this, we see that it is symmetric also, bilinear symmetric. There is no guarantee that it is no degenerate. Yes? Sometimes it is degenerate, so if it is degenerate, it cannot be used as a scalar product. And there is a concept of semi-simple Lie algebra. Some Lie algebras are, by some rather complicated definition, defined that they are semi-simple Lie algebras. And there also are simple Lie algebras. And Cartan, if I remember well, proved a theorem that the definition of semi-simple is independent now, yes? Cartan proved that if we take this independent definition and compare it with the scalar product which he invented altogether, independently of Killing, that he proved that if and only if the Lie algebra is semi-simple, this scalar product is non-degenerate. So we can now take it as a definition for us, that semi-simple Lie algebras are those Lie algebras which have non-degenerate Killing-Cartan scalar product, because it is true from some other definition. Because I don't want to go to some ideals of Lie algebras and so on. A little bit is written in the appendix in this book. There is an appendix Lie algebras, and you can learn what is ideal of Lie algebra and those things. But I don't want to introduce some big theory about Lie algebras. You can study books if you need. Just some elementary knowledge. And for elementary knowledge, it is enough for you to know that if you compute some Killing-Cartan bilinear form and you see that it is non-degenerate, you know that your Lie algebra is semi-simple. Because sometimes for some construction, you need semi-simple Lie algebras. So now, we introduce components, because it is, once more, bilinear form in G. So components are K computed on basis of Lie algebra. What is it? It is trace of adjoint operator from EI composed adjoint EJ. Now, what is trace? Trace is here, and once again, this is the basis of the vector space. So our vector space is Lie algebra. So the trace is also to be computed with this basis, the same basis. Yes? What is it? EK adjoint of EI, adjoint of EJ applied to EK. Now we should compute. This is a commutator. We derived the formula on Monday. So it is CJKLEL. Now, this is adjoint EI on this. It is linear, so it jumps over this and comes here. It is what? CJKL adjoint EI to EL. It is commutator EIEL. It is IL, some R, ER. And now this goes inside this and produces delta RK. Yes? So this goes outside, JKL, ILR, and here is EKER, which is delta KR, and delta KR means that those guys are summed. So I will write it first CI, then CJ, and here will be KK and LL. So this is the result. What is interesting and nice that whenever you compute these structure constants of your Lie algebra, from this formula you can directly compute the metrics of the Killing-Cartan form. And you can check whether it is nice or not nice, semi-simple or not. So, example, take SO3 as our Lie algebra. We know that in this basis we have structure constants from Lij epsilon ijk Lk, which is epsilon kij by cyclic permutation, and it should be Cijk Ek. So we see that this is this. So you can insert this here, compute a little bit. It is computation with 2 epsilons. So what is a Davis cup identity? Yes, and you get that it is minus 2 delta ij after short computation. So now the question is it good in the sense of semi-simple? Is it semi-simple algebra or not, our SO3? Cartan told us that semi-simple is K non-degenerate. So is our K non-degenerate or it is degenerate? It is non-degenerate because it is the matrix minus 2, minus 2, minus 2, 0, 0, 0, 0, 0, 0. Yes. Determinant is non-zero. We can, and it is usually done in this case, that now, what are good properties of this? A lot of good properties. Symmetric, bilinear, and so on. The most important I still have to tell. And if you take any multiple of this expression, it still has the good properties. So we can help to the scalar product a little bit if it is not perfect. Because now, for example, this minus 2 is not very nice here. Just delta will be nicer. So we can just obtain what minus 1/2 of this, if I compute correctly. So some help here by some number will give you just delta ij, perfect scalar product with respect to this basis. Yes. So the lesson that here could be some multiple and still it is nice scalar product. And also can be told that it is Killing-Cartan, it is some product of Killing-Cartan. And what is the most important property and completely not visible at the first? That the statement is that K is adjoint invariant. So it is an example of these interesting scalar products. So we had that H is rho invariant in our general theory. Now H is K and rho is adjoint rho. Very special representation from Monday. So this is a special case of this situation, and notice that it was not computing by some averaging over the group. It was directly defined. So they both noticed that this expression is interesting somehow. And they computed it, and they compute also this property. So what does it mean? As a formula, that if you compute this, and if you compute adjoint of G applied on X, and adjoint of G applied on Y, you will obtain the same number for all X, Y, and G. So this statement can be written here. And I will not do the proof. The proof is simple. It can be done in exercises easily. Even in the book, you will have something more complicated, namely that take any representation of G in V and think of other expression, rho primed of X, rho primed of Y, and trace of that, and call it some BXY. That for any representation, we can derive first the derived representation of Lie algebra. Here are operators in V now, so also the trace is also in V, with the basis of V, like there. And now the statement is that even, this is a special case for rho equals Ad and V equals Lie algebra. So Killing-Cartan is special case of this more general scalar product in Lie algebra, which is treated in exercise some number, quite easy exercise. You can compute Bij, and it is computed from these matrix elements. Maybe you remember that we introduced some rho AB, rho BA, or IJ. This is the result computation from this formula. That put it EI, something like we did already, and you will easily obtain this formula, special case of which is this Killing-Cartan formula. Where it is? It is somewhere. It is not there already. Here it was. And even for this more general case, one can easily prove, in this exercise it is done, that it is also Ad-invariant. So this is, Killing-Cartan is a special case, but very important. What's the time? Okay. Now, there are two constructions with representations. One of them is very simple, and it is so-called direct sum of representation. I will give it as an exercise. It is called this one. So the aim is, you have two representations. Can you construct somehow the third representation? Yes, this is one possibility, and a little bit more involved is the second possibility, which is called tensor product. And this is just a sum. This sum will be given as exercise. It is simple. This is also not complicated, but it needs a new concept which is similar to concepts which we already know, but it is not directly like that. It is some generalization, the generalization of tensors, in a sense. So I will speak to the very end of this lecture about this representation, that how it works, where it works, and so on. So if you have a representation of group, you need to specify when it works and how it works. So this representation, by definition, works in V1 tensor product with V2. And this concept was not introduced yet. It is a concept which can be done in full generality, and then it is quite involved. Nice idea, mathematical, but rather involved. Or for finite dimensional cases, it can be done much simpler way. So I restrict to, because we are speaking mainly on finite dimensions, I will only describe this finite dimension version, which is not so involved. It is also described, this tensor product is described in appendix. So if you do not understand something from here, have a look to appendix. Appendix number 1 already, linear spaces. There is this construction of, this is a construction of a new linear space out of two other linear spaces. So, my definition here, this simpler one, which by very wise mathematicians, they do not like it very much. They want to have the full general approach, but it, we will spend some, I don't know, 20 minutes or 30 minutes by this full general definition. You can find it if you are interested. But the simple definition that this is the space of V1 star cross V1, V2 star to R bilinear. So the element of this vector product is a bilinear map from here to here by this simpler definition. Now, it is similar to the concept of a tensor, if you have a look. That what is a tensor? Several L's times several L stars to R and multilinear. This is tensor of type PQ of L. So it is, you see that it is very similar. Of course, it can be also iterated, like here that many. You can put times V3 star and so on. Then it will be V1 tensor product V2 tensor product V3. Yes, we can do it also with more just two pieces. And we know that such mappings form a linear space. This was crucial for defining of tensors. That any tensors give you a linear space. And we can compute dimension. Dimension is n2p plus q, yes, of this linear space. So we can also try to do in the same way this example, that it is something, so the element, say W, from V1 cross V2 is a mapping from two covectors, but now it is very important that here are completely different vector spaces, arbitrary. V1, V2 is arbitrary. Here, it's just L and dual of L. So it is very restricted special case of this. But very similar. If we understand properly this theory, this modification to more general situation is quite easy. That if we have some element from here, we can insert what? Two covectors, some alpha and beta, but they are not covectors from the same covector space, but this is from V1 star and this is from V2 star. In general, and this is a number. So we already see that we can introduce components that if V1 we have a basis EA, so in V1 star we have a basis, dual basis EA. Here, V2 we have a basis some EI, in V2 star we have the dual EI. So we can now decompose this alpha, because it is from V1 star, it is decomposed with respect to this basis. this beta is some beta I EI, because it is from V2 star. And all results W alpha beta are known if the value of W on just basis is known. Yes, so we introduce EA, EI as components. If we know these components, we know all results. Now, these are components with respect to some basis, how the basis looks like. We introduce special W that some V1 cross V2, of course this is from capital V1 and so on. This on alpha beta is like tensor product was introduced. Think it over, that it is alpha is covector which eats V1. So let's allow to this alpha to eat this V1. And beta is able to eat V2. We have two numbers. This is the definition of this product. So if you have a vector from here and vector from here, you can make their tensor product, and you will obtain a vector from here altogether. Yes? So the special elements of this vector space to be introduced, or just introduced, are of this type. Yes? In particular, you can take a tensor product of the basis. Compute how it works. And then you can check that any W can be written as WAI EA tensor product EI. Most important result yet. So this is the most general element from V1, V2. Now, how many dimensional vector space it is? If this is n1 dimension and this is n2. So we see that how many numbers we need to fix some particular element. They are sitting here. There are n1 possibilities for A, independent n2 possibilities for I, so altogether the product. Dimension V2 is n1, n2, that means the dimension of V1 multiplied by the dimension of V2. So it is the product. So, for example, if you make tensor product of two-dimensional and three-dimensional space, you obtain six-dimensional space. It grows rapidly, yes, this dimension. So this is the dimension, this is the basis. And very important thing for our strategy to build a new representation is that there are specific operators in this vector space constructed from operators here and here. So imagine that we have some A1 in V1 and some A2 in V2. Yes. Now we can construct an operator A1 cross A2, which is called tensor product of these operators, by this definition, that it is a linear operator. So when it comes to this most general object, it jumps over the components. This is the definition of linearity of this operator. And here we apply A1 on EA cross A2 on EI. And notice that this can be computed because A1 is in V1, and this is the basis of E1. And here is A2 in V2, and this is the basis of E2. So these results are known, so everything is defined. And you should check yourself that if you define this kind of operators and multiply or compose two of them, that there is a simple rule that A1, B1 tensor multiplied by E2, B2. This is that check from the definition. And this is a very simple rule how to manipulate these operators. By the way, these operators and this structure is extremely important in the direction of science which is called quantum computing. If you want to study quantum computing, this tensor products and tensor products of operator is the alphabet 10 times a day. You use it. For very simple vector spaces usually, but a lot of them. Now, this is, so E1, E2 is an operator in V1, V2, and it is a linear operator. I do not say, and it is not true, that it is the most general operator here. The most general linear operators here are those plus others. This is just one family of operators. Because useful, because they are very interesting for many things, but far from all. They are operators in this vector space which do not have this structure. It is visible also from the counting of numbers, that how many numbers I need to define this operator. By this construction, I need to specify this and this. So I need a matrix of A1, which is N1, N1, and this matrix, which is N2, N2 numbers. So altogether, in this operator, I have N1 squared plus N2 squared numbers. They are just numbers of matrix elements of this and matrix elements of this, summed. And if you think that this is so many dimensional vector space, so general matrices are this squared, yes, and it is more than this number. So there are linear operators which are not of this structure, but we are not interested in these linear operators. We are only interested in this structure of operators because they have this property. Yes. Now we can go to a representation, to the definition, that if we know all that how to construct V1, V2, and especially how to construct these operators, we can define this guy. That very short definition is that this representation on of G is given by the tensor product of these two operators. Yes, this is the definition. That this symbol for tensor product of representation, when applied to element G, is tensor product of the individual operators of ρ1 G and ρ2 G. In which sense? In this sense. Yes. Now the easy check, is it a representation? Is there a vector space when it acts? Yes, it is V1 cross V2. Is it an homomorphism? This is a critical check. Yes. Is it a homomorphism? So, if we put G1, G2, or GH ρ2 GH. So what happens? First, this is a representation. So this is a homomorphism. It is rho 1 G, rho 1 H. Tensor product with rho 2 G, rho 2 H. And now have a look here where it is. Here, it is like that expression. Yes? There are 4 guys, like there. So we can go on and write the left-hand side of this. This rho 1 G times rho 2 G multiplied by rho 1 H, rho 2 H. But this is rho 1, rho 2 on G, and this is rho 1, rho 2 on H. Yes? So rho 1, rho 2 on rho 1, rho 2 on GH is this. This is this multiplied. So that's why this is a homomorphism. It behaves nicely on product. And this is all what we need, that we constructed really a representation, a new one. Tensor product of 2 old representations. Now the interesting story is that what is its derived representation? So what is rho 1 tensor rho 2 derived? Because this is, of course, the representation of the group G, yes? And the derived is always a representation of correspondingly algebra. So, first, derived representation always is defined in the same vector space like the original representation, yes? So it works or acts in V1, V2. How the general derived representation is computed? That computed is computed the original row on this element, and it always be of the form rho primed x. So this is the formula for computation in general of derived representation. So we should do this, the same thing. Maybe I will not finish it. Rho 1 tensor rho 2 on 1 plus epsilon x should be unit operator plus epsilon rho 1 rho 2 primed on x. Now, what is this? Where is the definition? Here is the definition. It is rho 1 on 1 plus epsilon x. I will not finish it, just write where it is. Cross rho 2 on 1 plus epsilon x. Here it is, it will come from this line rho 1 primed. Here will come from this line rho 2 primed. Then you should tensorially make product. And what is the result? I will write it here, that it is rho 1 primed x tensor with unit operator plus unit operator cross rho 1 primed x. And this unit is in the second space, so in V2, and this is unit in V1. You can finish the computation and you will see it. So the derived representation has two parts, and this is very important formula, that because
I think there should be row 2.
Row 2, thank you. Thank you. Row 1 here. So that's all for today. Okay, thank you.